This review video is meant to take a few moments to go over the concept of density and to also use it to talk about compound or derived units. So density is a measurement of the amount of mass, so that's going to be 1 unit, in a particular quantity of matter, and then also how much space that quantity of matter takes up. So that's our volume. Density changes depending upon the circumstance, particularly with respect to temperature, and we'll talk about that more in a moment. The formula for density, which is density equals the mass of the substance divided by its volume, can be found on table T of the reference table and needs to be memorized as part of the formulas that we hold in our minds. The way density and temperature relate to each other, which we'll look at in this graphical example in just a moment, and what is interesting to us in chemistry is the phases of matter and how they change based upon the application of temperature and therefore the change in their density. So solid substances are arranged in an orderly manner. They have a definite volume and they have a definite shape, and the particles that make up a solid are very closely packed together. The liquid of the same substance, so the next phase of matter, has a definite volume again, so I can measure the volume, think water in a graduated cylinder. But the particles are actually able to move past each other or flow, and that is due to the increase in space between the particles. So the density of the substance has decreased. Now, when you think about what happens when you go from a solid to a liquid, thinking about ice, for example, something we understand very well, ice melts when we apply heat. And when we apply heat, we increase the kinetic energy of the molecules or the particles in the substance, and therefore we increase the temperature. Similarly, if I look at the same substance in the gaseous phase, to go from a liquid, let's say water in a pot, to steam, I need to add heat again. The temperature is increasing and the density is decreasing. So what we can tell from this, and I'm just going to make this a little smaller so that we can see what's happening with the graph that we have here. You can see from the graph that we have an inverse relationship between density and temperature. So as temperature, which we will label our x-axis with, as our temperature increases, so this arrow down here represents the direction of increase, our density, which I'm going to write here and swing around so I don't have to write sideways, our density actually decreases because as we move up the y-axis, density increases, but you can see that as temperature increases, the point associated with density moves downward. Okay, so I become less dense as my temperature increases. So we would likely see substances in the solid phase here, in the liquid phase here, and in the gaseous phase here to relate that to what we've just looked at. So I mentioned that density is a compound or a derived unit, which means that it's actually multiple units of measure combined together to show a relationship. In the case of density, we're comparing mass and volume of the same substance. So the kinds of questions that we might see, here's a reasonably straightforward one, is what is the density of carbon monoxide gas if the particular sample that we're looking at has a mass of 0.196 grams, so that's our unit for mass, and 100 milliliters. So using our calculator, we do 0.196 divided by 100, and we get 0.00196 as our number. Now going back to the investigation of significant figures, right? When we divide or multiply numbers, we look for the smallest number of significant figures. In this case, that's going to be 1 because 100 has one significant figure. That means we're going to round our number to 0.002. I haven't put units in yet. And if we really want to practice, we can actually look at this with respect to scientific notation as well, and I can convert that to 2 times 10 to the negative third. No matter how I choose to report this answer, I need to make sure that I include my units, which is grams per milliliter. Okay, that is a measurement of density, my mass and my volume. Moving on to our next problem, right? So we would look at the problem number 1 is a way that we can determine the volume of a gas or a liquid. We're usually going to be measuring our volume in some form of liter, so milliliter, centiliter, microliter, kiloliter. And our mass is going to be measured in some derivative of grams. So kilograms or grams or centigrams, all of that is fine as long as we have a mass per volume. In the first example, we can also use this to determine the density of an irregular solid. So if I can't measure the length, the width, and the height of a solid because it doesn't have regular length, width, and height, I can use the method of displacement and then assume that the volume that the water has changed equals the volume in milliliters of the irregular solid, much like what we did in our measurement lab with the marble. In our second example here, we have a regular solid, and we're told that we have a block of wood. So this is similar to the process that you did in the measurement lab as well. And each side of the block of wood is 3 centimeters. So each dimension is 3 centimeters. Now, that's important for us to know because that is what's going to allow us to determine the volume of this cube. And that's going to be 3 centimeters times 3 centimeters times 3 centimeters, which equals 27 centimeters cubed. And if we really wanted to convert this to significant figures, 3 centimeters, 3 centimeters, and 3 centimeters means that I need to round my answer to 30 centimeters cubed, representing the appropriate number of significant figures. Because I don't know if I measured the block and it's exactly 3 centimeters or that's what my block has allowed. Now, in our examples that we might find in the future, you're probably going to get a couple of more decimal places. But in this case, we didn't. So 3 times 3 times 3 is 27, which we round to 30. Then what we can do is we take our mass, which is given to us as 27 grams. We divide that by 30 centimeters cubed, which is also a measurement of volume. And 27 divided by 30 is equal to 0.9. 0.9 is the same number of significant figures as our smallest number of significant figures, so that's convenient. And then we make sure to include our units of grams per centimeter cubed. Moving on to irregularly shaped solids, right? We just talked about the displacement method. We take an irregularly shaped stone, we lower it into a graduated cylinder holding a volume of water equal to 2 millimeters. So this is volume initial. Our initial volume, or VI, is equal to 2 milliliters. After I add the stone to the water, I then have a V2 of 7 milliliters. That seems a little hard to believe, to be honest with you. How do you turn 2 millimeters? Doesn't even seem like enough water to cover a stone of that size, but we'll go with it for right now. This is the example we have. And the point of the matter is that we're looking for the difference between, I'm actually changing that to VF, or volume final. We want to find the difference in order to find the volume of the irregular substance. So remembering that we always do final minus initial to find our difference, we're going to do 7 milliliters minus 2 milliliters, and that's going to give us 5 milliliters, which is the volume of our stone. Having found the volume of our stone, we can now complete our task of determining what the density of our stone is by taking the mass, which is given to us as 25 grams, dividing that by 5 milliliters, getting an answer of 5 grams per milliliter, and then seeing that that gives us the appropriate number of significant digits as well as our answer. Continuing on, a 10 centimeter cubed sample of copper has a mass of 89.6 grams. Well, that's another one of those very straightforward questions where we're taking the mass of 89.6 grams, dividing it by 10 centimeters cubed, and then that's going to give us, right, if we do that, 8.96 grams per centimeter cubed. Now, evaluating the number of significant figures, my numerator has 3, my denominator also has 3, my answer now has 3 significant figures, so we're good. The density of copper is 8.96 grams per centimeter cubed, or so we've determined. Doing a little bit of comparison here, we're going to move into talking about silver. I guess I should have saved that colored pen for this particular question, but we'll do the best we can with purple. So silver has a density. Now we're being given the density here. So silver, whose symbol is Ag, has a density of 10.5 grams per centimeter cubed. Gold, Au, has a density of 19.3 grams per centimeter cubed. So clearly gold is denser. You get more gold atoms in the same volume. So let's take a look at what's happening here. If we had a volume of silver and a volume of gold that were both equal to 5 centimeters, which one of those samples would have the greatest mass? So we're going to practice both our usage of density as well as our dimensional analysis skills here. So let's start with silver. I want to find grams. And the way I've written my density relationship is 10.5 grams, and that's really per 1 centimeter cubed. So for every centimeter cubed, there are 10.5 grams of gold, and that's at a particular temperature. Usually these things are done at standard temperature and pressure. I want my answer in grams, so that's good. So what I need to do is I need to figure out how to arrange my information about how much volume or what the volume of silver I have is in order to get that. So here's my second bracket. And if I have centimeters cubed in the denominator of my first bracket, then I'm going to want centimeters cubed in my numerator of my second bracket. I think I may have just said second bracket twice. In case I did, you mean first and second bracket. So now I can easily come in here, I can cancel my units of centimeters cubed, and I can calculate my mass of 10.5 times 5, which gives me 52.5 grams of silver. Okay, so looking at what's going on here, if I was going to be converting to significant figures, I would need to convert to 50 grams of silver. So we'll have that as our information for that. And then we're going to take a look at the next piece, right, which is determining how much mass of gold, or what the mass of gold I have is. Following the same procedure, I have the same volume of gold. So a gold cube that measures a certain amount on each side, right? And I'm going to do my math here. I'm going to cross out my centimeters cubed again. I'm going to do 19.3 times 5 this time. And that's going to give me 96.5 grams of AU. Again, if I had to round my answer, I'd have to round it to 100 grams of AU, because I need one significant figure, and I'm rounding a 9 with a 6, so that's going to give me 100 grams. And in comparison, you can see that I have nearly twice the amount of gold as I do silver. Now, by the way, if we go back and we look, 10 grams per centimeter cubed versus 19 grams per centimeter cubed is roughly a 1-to-2 relationship. So that's a nice little check there to see that we've probably done our math correctly. And finally, looking at question number 6 here, we have 5 milliliters, so that's a volume, of ethanol. Ethanol is the alcohol that is found in beer, wine, and spirits. It's one of the substituted hydrocarbons that we'll learn about later in the year. And its mass is 3.9 grams. So this is, let me just move this over so I can label that this is ethanol. We have another substance, benzene. Benzene is a hydrocarbon ring, and we are told that we have 5.0 milliliters of benzene with a mass of 44 grams. Now, before we even do anything, which liquid is denser? Many, many more grams of benzene exist in 5 milliliters than ethanol. So benzene is clearly going to have the greater density. So that's a good check to just sort of take a look and decide, is what I'm doing correct? Does it make sense? So we're going to set up our comparison here. 3.9 grams per 5 milliliters. And we're going to simplify by dividing 3.9 by 5, and that's going to give us 0.78. I need to round to one significant figure, and that's going to bring me to 0.8, and then grams per milliliter. Similarly, now we have 44 grams per 5.0 milliliters. Looks like we're going to have a different type of significant figure situation happening here. We're going to do 44 divided by 5. That's going to give me 8.8 grams per milliliter. My answer needs to be reported to two significant figures, so that works out well. And the answer to the question of which liquid is denser is benzene.